What's up YouTube? In this video I'm going to show you how to design steel reinforcement in reinforced concrete in under 5 minutes. This works whether you're designing a reinforced concrete beam, a retaining wall, suspended slabs, or even reinforced concrete ground beams. Just anywhere whether you've got reinforced concrete that is in bending. So there is literally no shortage of content out there in terms of how to work out the bending capacity of reinforced concrete. You can see from a snippet that I've taken from a textbook here, you typically have to work out where that neutral axis is. You have to work out the strain profile of both concrete and steel, and then work out the stress distribution, which for concrete in compression changes from that parabola shape, and then a lot of codes idealize it to a rectangular stress block to make it easier. And then work out the sort of the depth between those two, and you get the strain profiles. And to be honest, it's pretty tedious to go through all of this by hand. So that's not at all what this video is going to be going into. This is going to be an approximate method, which is more suitable whether you're doing a concept design or you just you're in a meeting and you've got 1 minute to just quickly do some sort of like a feasibility calc, or you just want to do a sanity check on what your SAFe or your software analysis packages are doing. So it's more something to do, like to design reinforced concrete without doing all of this tedious work. You just want to sort of do a sense check. So I've essentially got 3 steps to work out steel reinforcement in reinforced concrete. So firstly, there's you got to choose the depth of your member. Secondly, you got to work out the bending moment. And then the final step is to choose your steel reinforcement for that bending moment and depth. Okay, so I'm going to run through an example. Here we've got a simply supported one-way slab that's supported by some steel beams that I've sketched here. So the first step is to work out the depth of that slab. So the slab that I've got here spans 6 meters, and you can pick up any of these sort of like span to depth ratios, but it's essentially the first point in just quickly working out what to just approximately size the depth of your slab. So 6,000 divided by 20 for span on 20 for, as I just picked out of this textbook here, for reinforced concrete that's simply supported, gives me a depth of 300. Now for a simply supported slab, as we all know, WS squared on 8 gives us our moment. So I've just used a UDL here of 10 kilonewtons per meter. WS squared on 8 gives me 45 kilonewtons meters bending moment. So that's, essentially the second step in terms of I've worked out what the bending moment is. Now the final step is to essentially choose the reinforcement that's going in that 300 thick slab. So what I've done here, I've taken a section mid-span, which is that critical point of the bending moment, and I've taken a 1 meter strip of my slab. And as you saw on the first slide, it can get a lot more complicated than this, and that is because concrete is a lot more complicated than what I'm about to share here. But as for just like a crude method to just quickly do an approximate design or check someone else's work, or if you're just trying to, whip up some quick calcs in terms of what a rough number should be. A lot of textbooks here essentially estimate that the bending capacity is a function of the area of steel required times the yield strength of that steel times about 0.9 times the depth to the steel reinforcement. Note that this doesn't actually include any factors of safety yet. So that there should also give you a reminder when you're trying to increase the bending capacity of your slab that they're the things that really drive it. It's the depth of it as well as the area of steel reinforcement. So it's not so much dependent on the compressive strength of concrete. So I've put some numbers here for my bending capacity. I've got 0.9, and if it's a concrete cover about 40 mil, that's a depth of steel reinforcement of about 250. And now I just solve backwards for AST, which is the area of steel in tension. Subbing out those numbers, I end up with about 400 millimeters squared per meter, which is 2 N16s. And you know from experience that, for a 1 meter strip, having 2 bars is not going to be enough for crack control. So I've just called up here N16s at 300, which is essentially 3.3 bars per meter. And I'm just going to use that on the top and bottom for simplicity. So I've worked out from that approximate rule of thumb that I need about 2 N16s to satisfy the bending moment, and I've just upped it for serviceability, which is the next check that I'm going to show. which is, I also think, a really good way to just do a sanity check to know that your area of steel reinforcement is in the ballpark. So from the what I just showed before, I've got N16s at 300 top and bottom, which ends up being 3.3 bars per meter. And if you open up AS3600 here, this is, as I mentioned before, just a really good guide to do a bit of a sanity check to make sure that you're within the ballpark, or if you're looking at something else, just to know whether it's a sensible amount of reinforcement. You can see here I've highlighted a medium degree of crack control is 0.35% of steel reinforcement. So if I just want to see how much my N16s at 300 top and bottom are, I work out the area of steel, and note this is for the whole section, so it's not just the bottom layer or the top layer, it's both of them. I know that my area of steel for that section is 16s at 200 top and bottom. No, sorry, 16s at 300 gives me 1340 millimeters squared per meter. And then I simply divide that by the cross section. So I'm going a meter strip, and I got a depth of 300 that we got before of our span to depth. And I've got 0.45% reinforcement. And that places me between, that would be a moderate degree of crack control. So then, it's a sensibility check. You're within the ballpark. You're in between medium and high degree of crack control. So that's just another way to know, yep, that sounds sensible. And that's essentially it. I picked a depth off the span to depth ratio. I worked out my moment from, simply supported WS Gordon 8 bending moment formulas that we all know. And then I chose a steel reinforcement based off that approximate calculation, where it's just the area of steel reinforcement times the yield strength times about 0.9 times to the depth of the steel reinforcement. And I've just done a sanity check with crack control, the degree of crack control. And that's it. Then I'm done. My 6 meter simply supported one-way slab is 300 thick, and it's got 16s at 300. So note, this also doesn't include post-tension. Most suspended slabs will have post-tension in them, and that's why they'll be, for that same span, you'll probably get thinner than 300. They're just more efficient. But yeah, in terms of reinforced concrete, that's how I would do it.